Hello, Mr. Claudia here, and today we are going to continue studying limits, specifically one-sided limits. Today we're going to answer the question, what happens if the limit from the left and the limit from the right aren't the same? And the big central idea today is going to revolve around piecewise functions, which you, I think, have seen in a different course. I find that students tend to have the hardest time with not with the limit, but with the piecewise function. So let's just go over that first. Piecewise function has different pieces. So it's listed like this, right? And each of them has a matching domain. So for this curve, this function rather, it's a quadratic for all the x values less than 1. And then it's a linear, it's a line, for all the x values greater than 1. So this is the mother quadratic, it's centered at 0, 0. So it looks something like this. And that's including 1. So at the point 1, 1, there's actually a point there. And then this is a quadratic. It's a slope down, and it crosses the intercept, or it crosses the y-axis at 3. So it's up here, and it actually doesn't include this point. So it looks something like that. The y-intercept is here, right? So it doesn't include the y-intercept, but it starts off down here. I believe this is at 2, and this is at 1. So that's a piecewise function. Is it still a function? Yes, because it passes the vertical line test. At point x equals 1, it only has one value, that is 1. There's a hole here, so you can almost imagine that it kind of jumps to the next point, but it only is equal to, the function is equal to x equals to y, the function is equal to y equals 1 when x is equal to 1, right? That's what that tells us. If this hole was colored in, then it would not be a function because it would fail the vertical line test. So this is our piecewise function. What is the limit of this function as x approaches 1? Well, there's x equals 1 there.
Miss Mieta, colon 101. Miss Mieta, 101. Thank you.
Up till now, I've been editing out some short announcements, and I'm not going to anymore. So you just heard that one. Okay, so x equals 1. Okay, so we want to know the limit. Remember, the limit is not what happens at x equals 1. It's what happens as we get closer and closer and closer to x equals 1. So let's start by approaching from the left, just like we did yesterday. So I'm going to be driving along this curve, and I'm going to get closer and closer to x equals 1. So I'm going to choose some x values that are smaller than 1. So 0.9, 0.99, 0.999. These are getting closer and closer. Then I'm going to sub these into my graph, or into my equation. Now, which equation am I going to sub them into? Well, this equation is valid when we're dealing with x is less than 1. So I have to use the parabola. So I'm going to sub the x values into this parabola equation. So 0.9 squared, for example, is 0.81. If you keep using your calculator, you can fill in the remainder of these points. So what do I find? As x approaches 1 from the left, the limit is 1, right? It's getting closer and closer to 1. Okay, let's now finish our study of this limit. What happens as I approach from the right? Okay, well, I'm going to choose a bunch of x values that are getting closer and closer and closer to 1, but they're larger than 1. And the function I'm going to be looking at, well, when x is greater than 1, I have to look at this function, 3 minus x. So I'm going to sub in these values. So I have 3 minus 1.1. That gives me 1.9. I can keep typing those into my calculator, and there are my answers. So what does it look like as x approaches 1 from the right? The limit is, well, it's getting closer and closer to 2. Remember, the limit, I don't care what happens at x equals 1. I care about what it looks like is going to happen. And graphically, this is pretty obvious. As I approach from the left, looks like I'm going to be at y equals 1. As I approach from the right, it looks like I'm going to be at y equals 2. And that's exactly what I found when I subbed in values. So, the way I write these words mathematically is like this. The limit of the function as x approaches 1, and I have that negative there. That negative is called the left-handed limit. In other words, it means that you're approaching from the left. So in this case, the left-handed limit is equal to 1. And on this side, I have the limit of the function as x approaches 1, and there's a little plus there. That's the right-handed limit. Well, if the and that's equal to 2. And here's our fundamental thing with the limit. The limit from the left and the limit from the right have to be the same. And they're not. So then we say the limit does not exist. Let's write that in math lingo. Since the left-handed limit, x approaches 1 minus, of this function does not equal the right-handed limit of this function, therefore the limit as x approaches 1 of this function does not exist. So there's a lot of notation there, but essentially because these numbers are the same, or sorry, these numbers are different, the limit doesn't exist. The limit everywhere else on this function exists, right? If I wanted to know the limit as x approaches -2, it would exist. If I wanted to find the limit as x approaches 0, as x approaches 8, they all exist. It's just this point. And graphically, I can see this, right? From the left, from the right, they're not meeting. This is a weird graph where these two pieces don't meet. So what I intuitively know is a step here. The limit is the mathematical way that I can explain that to somebody. And so there's just our definition. If the limit from the left and the limit from the right are not the same, then the limit does not exist. In other words, the left-handed limit and the right-handed limit must be the same. Okay, let's do another question. Let's look at question 2, this example, which is the Heaviside function. Heaviside function is very important. It comes up a lot, like for me in third-year university when we were looking at signal processing. This is what you put into a function to simulate an on-off. So it essentially is 0 before time 0, and then it becomes 1 at time 0. So it's a super simple function, but it tests an on-off in a function, or in a system. Heaviside. I think the guy's name was Oliver Heaviside, who invented it. But you can go check that. You can go fact check. So let's look at this function. What's the limit as t approaches 0 from the left? Well, I mean, there's a few ways you could do this. Let's say you don't have the graph. What you can do is you can do direct substitution. So for t is less than 0, the function is equal to 0. So therefore, I'm really looking for the limit of the function 0, which is going to be 0. Again, how did I do that? Well, this Heaviside function, it could be this or this. But if I'm looking at t approaching 0 from the left, then t is less than 0. So I'm going to replace the h at t with this function 0. So now I'm just looking at the limit of 0, which is just 0, right? If it's a number, then I just use the number. Similarly here, this is the limit, the right-handed limit. I'm going to replace h at t with the value of the function when t is greater than 0, which is 1. For t greater than or less or equal to 0, the Heaviside function is equal to 1. So therefore, I'm really looking at the limit of 1, which is 1. Well, does the actual limit of the Heaviside function as t approaches 0, what can you tell me about it? Well, because from the left and the right, they're not the same, then the limit does not exist. Since the limit as t approaches 0 negative h at t does not equal limit h at t from the right, then therefore the limit as t approaches 0, the Heaviside function does not exist. And again, if you had the graph, it makes sense. If you approach 0 from the left or the right, you can see that they're not going to be the same. Okay, here's a fun one. The limit of the absolute value function. Well, Mr. Claudia, I thought you said we were doing piecewise functions. Now you're just giving me absolute value functions. Well, if you remember the piecewise function, let me just get my ruler. Sorry, the absolute value function. You guys remember this is almost like a line and a line. This is the absolute value function. Now, the absolute value bars are kind of weird. Like, we don't know how to, they're hard to deal with when we're doing algebra and hard to deal with when we're doing calculus. So what we're gonna call this what it is. F of x equals the absolute value of x. That really means f of x equals negative x, so it's a negative, it's a line with a negative slope for all the situations where x is less than 0. And it's x with a positive slope where x is greater than or equal to 0. I just chose the equal to 0 in this case. That's really what we mean when we write this. It's a piecewise function. It's a line and a line. So now I want to find the limit at this point as x gets closer and closer to 0. Now in my heart of hearts, I know the answer to this is 0, right? The limit from this side is 0, the limit from this side is 0. Let's see if I can do it mathematically. I have to look at the limit as x approaches 0 from the left. Okay, well, from the left I'm looking at this function. So I'm going to replace the absolute value with negative x. So the limit of negative x as x approaches 0. Okay, if you do a direct substitution now, you end up with 0. Similarly, let's look at the right. The limit as x approaches 0 from the right of absolute value function. Well, I go to my absolute value function. For positive values of x, I use x. So limit of x as x approaches 0. Then I do direct substitution. I sub in the 0. It just works out. So there we see this one is a good story. Since the limit as x approaches 0 from the left of the absolute value function is equal to the limit as x approaches 0 from the right of the absolute value function, therefore the limit of the absolute value function as x approaches 0 is equal to 0. That's really our lesson, one-sided limits. It's just an extension of the limits lesson. Graphically, it's really easy to figure out limits, but algebraically, it's useful to, well, this is more of a proof, but it's useful to be able to look at the limit of the left side and the right side by replacing the function. So this strategy down here is a useful strategy. It's good for us to understand what we're talking about. Now we can just talk about these important calculus terms, continuous and discontinuous. A continuous curve, or continuous function rather, is a smooth curve with no breaks and interruptions. This is the curves you know and love from, grade 9 and the beginning of grade 10, simpler days. Just a smooth curve like this polynomial here. Those curves that you've been seeing, you started to see, and we see a bit more now, the curves that have breaks, or jumps, or gaps, these are discontinuous functions. So something like that we have a name for it, right? Graphically, you can see there's something different about this graph. It's discontinuous. But we should still treat them like functions because they still are functions. Okay, now function f is continuous. So we define continuity mathematically if the limit as x approaches a is equal to f at a. So look what this says. If the limit of a function at some point is equal to basically direct substitution, then we say that the function's continuous. So if you think back to your quadratic, well, the limit at any point is the same as just subbing in the value at that point. What we saw yesterday and today is that doesn't necessarily ring true for a question like for this function. If I sub in this x value, I get this point, but the limit actually doesn't exist here. It exists everywhere else, but not here. So there are two things that need to be true from this statement. In order for something to be continuous, f at a has to be defined. So there actually has to be a point there. And the limit as x approaches a of f at x must exist. Maybe it might be useful if I have my note here from yesterday. Remember a note from our last lesson. Here was an example of the limit existing, but the point doesn't exist here. There's no value of the function at x equals 3. So this is also not continuous. It's not a nice quadratic, right? There's something missing here. There's a hole. In this case, the limit exists, but the value of the function doesn't exist. So it doesn't pass this first this first requirement. So now we can, with these two kind of truths that have to exist, we can look at all the different types of curves that we've seen. So one is your standard polynomial curve. So if I want to look at the limit at any point on this curve, I need to check, if I want to talk about continuity of this curve, I have to look at every point and say, is f at a defined? So if I look at any x value, is it defined? Yes. There's always a y value for every matching x value. And does the limit exist? Well, yes. At any point, the limit exists. Again, if you want to just think about the idea of the limit, if I were driving a car toward a point, is the car going to arrive there? Or does it look like it's the same arrival point from the left to the right? And yes, it does. So because you have those two things, your curve is continuous. Okay, second example I'm going to draw for you is a curve like this, like the one we saw today. Piecewise function. Now, is the function defined at all points? Yes, 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 yes. Here, at this point, x equals a, it's still defined. This is the value of the function. So it's always defined. But what we found today is the limit driving from the left is not the same as driving from the right. So the limit does not exist. I'm going to put a big X there. This means it is not continuous the entire time. It's continuous here, continuous there. It's not continuous here. We say that there is a step or jump discontinuity. At x equals a. So just at this one point. Okay, the next curve is something looking like what we did yesterday. If I have a hole here. So in this case, the function is undefined at this point, at this one point. It's defined everywhere else, but it's not defined at x equals a. Does not exist, in other words. If you were the helicopter there, you would land on the road and you would fall because into the lava below. Now the limit does exist, as we saw yesterday. If I approach from the left, it looks like I'm going to get here. If I approach from the right, it looks like I'm going to get here. Because the limits are the same, left and right, the limit exists. Now, this is not continuous then. This is a point discontinuity at x equals a. Finally, the last type of curve you could have is something like this, where you have an asymptote at x equals a. And you have a curve that goes like this, and the curve that goes like this. Okay, so in this case, at x equals a, is there a value to the function? No, it's undefined. What about the limit? Well, the limit, there is actually no limiting at all here. As you get closer and closer to x, the y value goes up and up and up and up. It goes toward infinity. So no, there's no limit. The very idea of a limit does not exist here. This is also then discontinuous. It's an infinite discontinuity at x equals a. Again, all the other parts might be continuous, but there is a discontinuity here. These are all still functions, but they're not all continuous. Why is this important? This shows us how we can use the limit to decide if something is continuous or not. Continuity can be important when we're finding derivatives, when we're doing calculus. We have to know if something's continuous, if we're going to be able to take a derivative of it. The last little note I'll make here is I'll point out that many of our favorite functions are continuous for all points. Think about all of the functions in the function family. What are the ones that are continuous all the time? Like f of x is equal to x, f of x is equal to x squared, f of x is equal to a to the x, that's the exponential, not absolute value, maybe a trig function. Your homework is, it's a separate sheet, number 1, 2, 3, and 4, A, C, E, G, I. Good luck with the homework, and see you next time.